okay? We're going to try and find these two LaGrange points. So we're going to start off, and I'm going to kind of get you to a point, and then we're going to diverge. And I'm going to show you the two different ways that you can solve the problem, depending upon what you want to do. So here's the basic idea of this first LaGrange point. That here's the lunar command module. At some point, the force between the Earth and the lunar command module is going to equal the force between the moon and the lunar command module. So it's like two dogs pulling on a rope, okay? So we want to find that point where those two forces are exactly balanced off. So we're going to go old school, F equals big G. So the first thing I want to find is the force between the lunar command module and the Earth. Okay, that's the first thing I'm going to try and find. So that's going to be the mass of the Earth times the mass of the lunar command module. Now, I tell you that the total distance between the Earth and the moon is 3 point, whatever that number is, 844 times 10 to the 8th meters. So that's the entire distance, okay, from the Earth to the moon. The number's actually getting bigger. The moon is actually drifting away from us, okay? Don't flip out. It's not much, but it is drifting away from us. So I'm going to let the distance from the Earth to the lunar command module be x. But that's going to get squared, okay, because it's an inverse square relationship. Now, that has to equal big G, the mass of the moon, times the mass of the lunar command module. So what am I going to do for the remaining distance? Well, let me ask you this. Chuck borrowed 20 bucks from me. He's paid me back 15. How much do you still owe me, Chuck?
5.
How'd you get that?
20 minus 15.
So if x represents this, and this is the total distance, how are you going to get the remaining distance? Subtract x, right? True? You owe me 5. You still owe me 5 bucks, right? So this is going to be 3.844 times 10 to the 8th minus x squared. Okay? Still squared. Still squared. That's huge. Now at this point, let's see if we can simplify things. Mac, is there anything that I can cancel out on both sides of the equation?
The mass.
Of what?
The
Yep. So that goes away. Why did I not give you the mass of the lunar command module in the problem? Doesn't matter. What else can I cancel out?
Big G. Big G.
Oh, I get rid of my big G. That's gone. Now, you all know my aversion to fractions. So at this point, I'm going to cross multiply. So I'm going to have the mass of the Earth times 3.844 times 10 to the 8th minus 10 to the 8th minus x, quantity squared, is going to equal the mass of the moon times x squared. Okay, all I do is cross multiply. Nothing fancy. I cancel things out. I cross multiply. Now, to make this simple, because I actually want numbers, I'm going to divide both sides by the mass of the moon, because that way I can get x squared by itself. So on your calculators, pull up the mass of the Earth and divide that by the mass of the moon, which is 7.35 times 10 to the 22nd. It's 80, it's around 80 if I remember right.
I got 81.3.
Give me two decimal places.
35.
81.35.
Oh, I got you. Okay.
So what that means is that the Earth is 81.35 times more massive than the Moon is. Okay? That's what that number basically tells you. Now, here's going to be your options. Okay? Here's where you have to choose a path. I'm going to show you both paths. You choose one. Okay? Now, option number one, you're going to use this and you're going to work this as a quadratic from the depths of algebra hell. Okay? I'm just telling you. So, let's do a quick refresher. Let's say that I gave you the quantity x minus 2 squared. What would you get when you would expand the quantity x minus 2? X squared minus 4x plus 4, right? Times 5. Then you'd have to distribute the 5, and then you've got an x squared over here. Then you're going to use the quadratic. To use the quadratic, what does one side have to equal? 0. So you'd have to distribute the 5, move that x squared over there, and then plug that into the quadratic. Negative b plus or minus the square root of b squared minus 4ac all over 2a. So if you're president of the quadratic club, okay, like your nickname was 2a in high school, okay, because you were that much into the quadratic, here's what you could do. So this is why I said this would be the quadratic from the depths of pain. So you would have to expand this binomial, okay? But instead of using x and 2, you're going to use 3.844 times 10 to the 8th. So you're going to square this number, get the numeric value. You're going to multiply it by 2 to get that value in front of the x, and you're going to have your x squared. Then when you get done with that, but wait, there's more. For additional shipping and handling, then you're going to distribute the 81.35 over all of that. Then you're going to subtract an x squared to get one side equal to 0.
Option 2, please.
Just chill out. I'm not done yet. Then, once you get all those numbers, then you're going to plug that into the quadratic formula. So, that's an option. I'm just telling you it's an option. You decide if it's a good or bad option. Here's option number 2. Okay? Option number 2. Could I, mathematically, legally, morally, ethically, whatever, could I take the square root of both sides?
Okay, yes.
Like that, Chuck?
Yeah.
So somebody give me the square root of 81.35. 9.02. But that's...
It is 9.02.
It is 9.02. Okay? But that's plus or minus. Okay? That's plus or minus. This is going to be important. That's plus or minus. So then you got 3.844 times 10 to the 8th minus x equals x. So here's how you're going to get your two possible solutions. Situation number 1, you can take a positive 9.02 and you're going to distribute it over this. You've got an x over there. Combine all your terms. It's an algebra problem. Get all your x terms on one side, get your numbers on the other. Then you're going to work it a second time. You're going to distribute the negative 9.02. Okay? But then you don't have to do the quadratic. So, if you want the most challenging quadratic problem you could ever hope to do, use the full numbers, expand the binomial. I'm just telling you, okay? Don't kill the messenger. I'm just telling you that's an option.
I don't like.
Or you can distribute a positive 9.02 and then work it a second time and distribute a negative 9.02. If you do this right, here's what you're going to get.
Does that give us both distances?
Yes.
Oh my.
Because you're distributing a positive and then you're
Negative?
distributing a negative.
Whoa.
Whoa.
Whoa, indeed.
Woe indeed. Woe is us. Woe is indeed. So L1, this is going to be your L1 value, which is going to be between the Earth and the Moon. The L2 value is going to put you out here on the other side of the Moon's orbit. So on number 7, if you do this right, you're going to get two answers. Both of them are 10 to the 8th. One's going to be inside the moon's orbit, the other one's going to be outside the moon's orbit. Okay? So that's going to be your two possible solutions. So if you want, again, if you want to work it as a quadratic, that's cool. If you want to shortcut it, you can, whatever works for you. Now, let's talk about where Newton intersects Kepler. So if you look, and this is a problem out of the book, and this is problem 42. So I'm going to work 42 right now out of the book. Okay? So if you look at that problem, planet X orbits the star Omega with a year that is 200 Earth days long. Planet Y circles Omega at 4 times the distance of planet X. How long is a year on planet Y? Okay? So I would start with a visual. Going, okay, you've got, here's the star Omega, and you got planet X here, and you're told that planet X, as it orbits around, takes 200 days. Okay? You're told that planet Y is 4 times the distance. So planet Y is 4 times that distance and is out here. Okay? Now there's a whole bunch of information that you don't have. You don't have the mass of planet Omega. You don't have the actual distance to planet X. You don't have the actual distance to planet Y. And you don't have the orbital period of Y. So like for example, if you look at 4 pi squared r cubed equals big G mass of omega t squared, you couldn't do that problem. You have too many unknowns. You don't know the actual radius, you don't know the mass of omega, you know the orbital period of 200 days, but then you're going to have 2 unknowns. So what we're going to do is we're going to go Kepler mode. We're going to go Kepler mode, because Kepler's going to go, hey, I didn't know the distances either, but ratios are cool, okay? So Kepler's going, let's use Tycho's data that I just stole. Let's see what we can do. So what Kepler is going to do is he's going to set this up as a ratio. He's going to say, okay, I'm going to let this be the radius of planet X. There's the mass of omega. There is the period of X. Okay? I'm going to set this as a ratio between these values. So that's going to be X. And I'm going to divide, because this is a ratio, then I'm going to do the same thing for planet Y. So I'm going to have 4 pi squared, radius of Y cubed, equals big G mass of omega times the period of Y squared. Cool. What's going to happen? 4 pi squareds, gone. What else is gone? G is gone. What else is gone?
Mass of omega.
Mass of the planet. What are you left with?
Yeah, how many?
Rx cubed over ry cubed equals tx squared over ty squared, otherwise known as Kepler's third law. So according to the legend, a contemporary of Isaac Newton comes to him and he says, hey, you know, you've done all this work with gravity, there's Kepler's laws, but we really don't know how the two merge together. Okay? And according to the legend, Newton pulls out a drawer of his desk, pulls out this piece of paper and goes, this is why it works. And he did something very similar to this, where the masses all canceled out. And he goes, and basically the guy says, why haven't you told anybody about this? And Newton basically says, I had other things to do. You know, I'm working on calculus. This is just a simple ratio. It's not that big a deal. So when you get to a question like number 42, you can use Kepler's laws, or Newton's laws, to arrive at Kepler's laws. But you're going to set it up as a ratio. So this is why you weren't given the mass of the star, because you don't need it. But here's the bigger truth. This is why this only works for objects that orbit the same center. This is why I can use this to compare the orbital periods of the moons of Jupiter, because they all orbit Jupiter. But I couldn't use Kepler's laws with our moon and a moon of Saturn, because they don't orbit the same center and the masses wouldn't cancel out. So that's why this only works when you have things that are orbiting the same center, because that's the only way you get the mass to cancel out. Okay? Cool with this. That's basically Newton says, here's Kepler's law. There you go. Okay. So your answer to 42 should be around 1,500 days. Okay? That's an ish, but it should be somewhere around there. Okay? Now, let's talk about 43. The next problem there. So let me kind of give you this visual on 43. So here's a star, and you got satellite A, here's A, and it's moving at 10,000 meters per second. And then satellite B is twice as massive as satellite A, and it is moving twice the distance. So if this is this distance, this is going to be B's, which is going to be twice that. There's going to be B, and you're going to try and figure out the velocity of B. Now, before you start this, why were they a jerk and they told you that satellite B has twice the mass? You don't need it. You can't plug the mass of the satellite into these equations at all. Okay? The fact that that satellite has twice the mass has no bearing at all. That's like saying, oh, it was made by Boeing. Doesn't matter. Great. Boeing built a satellite. Cool. Not part of the equation.
Let's see how that works out.
So, again, put yourself in Kepler's mood. What are you going to try to use? Ratios. You're trying to use ratios. You have velocities. So here's what I would recommend. You know that the velocity of A is going to equal the square root of big G, the mass of the star, over the radius of A. Okay? That's how you're going to calculate that, right? Cool. Then the velocity of B is going to be big G, mass of the star, over the radius of B. Now, this is where you got to get a little bit creative in terms of your math. Could I write this as the square root of big G times the mass of that satellite times the square root of 1 over RA? Is that legal?
Yes, that should be legal.
Mathematically, ethically, everything. I can do this, right? It's not violating any laws at all. Could I do the same thing down here?
Yes.
Big G, mass of the star, times 1 over RB. If I do it this way, and this is why I do it this way, what's going to happen to that constant?
The constants go.
Constant goes away, right?
Hey, you should do
Now,
what it is.
you know the velocity of A. You were given that number, 10,000 meters per second. You know that number. B, you don't know. And you don't even know the radius of A. But it's a ratio. So if you're clever, what are you going to let the radius of A be?
1.
1. So what are you going to let the radius of B be, so to speak? 2. So then it turns into more of an algebra problem. How are you going to isolate the velocity of B? Let me give you a hint. I hate radicals, so I squared everything and then I cross multiply. So if all goes well on 43, you should get an answer around 7,000 meters per second. Okay? All right, so there's one other one that I really want to get you started on, and that's question 57. Okay? So on question 57, you have what's called a conical pendulum. So on a conical pendulum, where's my rubber stopper? Here it is.
Wait, what question?
57. So on a conical pendulum, you have a morph of two ideas. It isn't purely horizontal motion, nor is it purely vertical motion. Okay? So you're morphing them into a situation like this. Okay? So you're going around like this. So you're moving in a circle, but obviously gravity is a key part of this story. So you have to start with this idea. So here's this string, and there's the mass that's on the end of it. So as this thing is like this, going around like this, there are only two forces acting on that pendulum. There are only two external forces acting on that, the end of that. What's one of them? Gravity. So I got gravity pulling down. So if you look on that one, you're told that it's a 500 gram ball. 500 grams times kilograms times G, you get 4.9. So you know that's 4.9 newtons. Okay, so that's one force. What's the only other force acting on that ball? Nope. Not there. Tension. You have tension. Now, is centripetal force going to be a component of that tension? Yes. Just like the hanging sign ladder. Okay? So, the tension is the overall component, right? But it's going to have a vertical component, and it's going to have a horizontal component. Okay? So Thatcher, what's that horizontal component? What's that going to create? What's the inward force?
Like the number?
No. Just what are we going to call it? Centripetal force, maybe?
Yes.
Yeah. So the horizontal component of that tension is going to be that centripetal force. What's the value of this going to be relative to 4.9 newtons? Do not make this difficult.
Approximately the same. If it is not in the same, then it is changing.
Stop at the same. So that's going to be 4.9 newtons. So the only number that you know is this. But you're clever, because you're also told that the string is 1 meter long. Okay, so you know the length of the string, 1 meter. You're told that it has a radius of 20 centimeters. Okay, cool. So if you know that's 1 meter and you know that's 20 centimeters, you can do some trig. Oh, you can find some angles. If you know some angles and you know one side of the triangle, guess what? You find everything else. So, the book gives you a completely, if you're one that looks in the back of the book for guidance on your answers, the back of the book on 5B is I don't even know where they got the number. It makes no sense whatsoever. So on 5B, it wants you to figure out what's the speed of the ball. So on 5B, you want to use centripetal force equals mv squared over r. So you're going to find mathematically the centripetal force. You're going to know that number. You're going to find it. You know the radius, you know the mass of the ball. You're going to try and find the velocity. Your book gives you like 30, as an answer of like 30 revolutions per minute. I have no idea what they were taking when they said, oh, that's an answer. Because it asked for speed, and they give you 30 revolutions per minute. So don't trust the book on that. I will tell you this, your answer to 57B should be around 0.5. Okay, that's an ish, but it should be somewhere around 0.5. Okay? So just keep that in mind. Anyway, all right.
Oh, that's all.
I'm done. So you have the rest of the time to work on this. So here's the plan. We're going to review on Monday. This test is going to be on Tuesday.
You better have your paper in by Tuesday.
And yeah, if I don't get that assignment on Tuesday, I'm not grading it. So,
Uh-oh, Colin.
oh yeah, we've already had that talk. Yeah,
But you should have had it.
we've already had that talk. So,
I was broken.
anyway, all right,
He's not.
you're on your own, so.
At the same time.
Honestly,
Procrastinate.